Hello everyone, I'm João from That's Brilliant. In this video we're going to talk about the derivative of e to the x. And we have a video in That's Brilliant in which we prove the derivative of e to the x. It is the first video proving this. And this is the second video in which we're going to prove the derivative of e to the x in a different way. So I'm going to put the link of that video, the first video proving this, in the description below. So let's start. First of all, what is e? Let's remember, e is a number. It's a constant. So it has a fixed value. And it is approximately 2.7. We can define e using a limit. So we can say that e is equal to the limit when, for example, m approaches infinity of 1 plus 1 over m, all of this raised to m. So this is a way of defining e using limits. So imagine we have a function f of x equal to e to the x. So in this video we are going to prove the derivative of this function. So we want to know the f prime of x of this function. So we're going to prove this using the formal definition of derivatives using limits. The formal derivative that uses limits to define what is a derivative. So we know that if we have, let's go on here. If we have f prime of x of a function, we have a function f of x. F prime of x, which means the derivative of that function, is the limit when h approaches 0 of f of x plus h minus f of x, and all of this divided by h. So this is the definition of a derivative using limits. So let's use this. We are in our context here. F of x is e to the x. So this is equal to the limit when h approaches 0 of if f of x is e to the x, f of x plus h is e raised to x plus h minus f of x. F of x is e to the x. And all of this divided by h. So we can continue here and we can use a property of exponents. So we can say this is the limit when h approaches 0 of e to the x times e to the h minus e to the x, and all of this over h. What I did here is use the property. When you have a multiplication of same base and different exponents, not necessarily different, but you have multiplication of the same base, we can use the same base. The result is going to be the base, and the exponent is going to be the, we're going to add the exponents. So we have a base raised to an exponent, that is a number plus another one. We can put this, a number with the first base times a number with the second base. This is a basic property we study when we study exponents. So, going on. This is equal to the limit when h approaches 0, and we're going to extract the e to the x factor. We're going to put e to the x in evidence. So e to the x, which multiplies e to h, minus 1. And all of this divided by h. So notice here that our limit is happens when h approaches 0. So our limit depends on h. And we can see that e to the x doesn't have an h there. So we can take this e to the x out of the limit. So this is equal to e to the x, and then the limit when h approaches 0 of e to the h minus 1 divided by h. So, we are going to work with this limit here. So, let's continue our math. This is equal to e to the x. Our e to the x is going to remain here for a while because we are going to work with this limit here. We are going to keep in our math here, so e to the x is going to appear a lot of times in the same place without changing. But let's go on. We are now use another variable. So we're going to define that u is equal to e to the h, e raised to h minus 1. So this is the limit. And now u is approaching what? Let's see. When h approaches 0, we can see that u approaches 0 as well. Because imagine, e raised to 0 is 1. 1 minus 1 is 0. So when h approaches 0, u also approaches 0. So this is the limit when u approaches 0 of u, because e raised to h minus 1 is u, divided by h. And now what's h? What's h? So let's work with this equation here. So we know that we can add 1 to both sides. So e to the h is u plus 1. So we know that h here is the exponent to which we raise e in order to obtain u plus 1. So we can write that h is the natural log of u plus 1. Natural log base e. So h is the logarithm base e of u plus 1. So e raised to u plus 1 is h. We can see that this is true in another way. Put in the place of u, put e to the h minus 1. Minus 1 with plus 1, they cancel, it's 0. And what is left here is e to the h. So the natural log, the log base e of e to the h is h. So this is true. So here we have under u over natural log of u plus 1. Let's go on here. Our ex, our e to the x remain the same. And we have the limit when u approaches 0. And now, we're going to do a math manipulation here. So this is going to be 1 over, now 1 over u times natural log of u plus 1. And why we can do this? We have a number here, the denominator of the fraction. We can put this down, we can put this in as a denominator, raising it to -1. So, multiplying by u is the same thing as dividing by 1 over u. So, this is true. This is just a math manipulation. And now, we're going to use another property of logarithms. That is, we know if we have, for example, let me use another color. If we have log base a of b raised to c, we can, this is equal to c log base a of b. This is a property we see when we study logarithms. If we have an exponent with the argument of the logarithm, this logarithm is equal to that exponent multiplying the logarithm. So it's kind of this that happened. We put the exponent multiplying the logarithm. This is a property of logarithms. And here we are going to do the opposite direction of the property. Instead of taking an exponent in front of the logarithm multiplying it, we are going to do the opposite way. We are going to take something multiplying the logarithm and putting it as the exponent of the argument of the logarithm. So let's do that. So this is equal to e to the x times the limit when u approaches 0 of 1 over natural log of u plus 1 raised to 1 over u. 1 over u is the exponent of u plus 1. And now we're going to use another variable. Let's create the m variable. So m is going to be equal to 1 over u. We can see easily that when u approaches 0, m approaches infinity. When u gets closer and closer to 0, m gets bigger and bigger. So when u approaches 0, m approaches infinity. So this is equal to e to the x times the limit when m approaches infinity of 1 divided by the natural log. Now we can put this way. We can, in this equation here, raise both sides to -1. So we have that